Good afternoon to those in Europe. Good day to those in other parts of the world. This is the webinar organized by the BS Communications Group on carbon capture as a way to improve the marine vessel performance. The webinar will take approximately 90 minutes. And we will cover the subject in quite detail, hoping that we are able to provide you an objective opinion on where we are at the technology development and what you can expect from carbon capture activities in the coming period. My name is Elias BOLETIS, and I have with me two colleagues, Joni. Mr. Joni Uolamo, who is attending from Finland. Joni will present himself and the company at his presentation, and Dr. Dimitris Koutsaftis representing ERMA first, and he will also give a presentation, a short introduction to himself and the company at his session. How we organize the meeting? We will have a few polls questions. You find the questions, the poll questions at the upper right side under the section polls. You find our 5 questions that you would be able soon to provide to submit your vote, and we will discuss it into detail after the main presentations. You will see also the function chat, where actually you would be able to add your questions that we try to answer from our side. We will answer the questions either by providing you a written answer, or we will discuss it with the panel members in our discussion. But be sure that we will certainly provide you with an answer. We will provide an answer to all questions asked at the meeting. So this is where we are, and I believe we are quite ready to initiate the presentations and start from the presentation of our material. The presentations which are given by the 3 presenters, Joni, Dimitris, and myself, will be made available by the organizer for you. So the presentations will be given to you at the end of the session or some short time later. Then give me the chance to start my presentation. I need also to say that you see the questions. Please vote. Your opinion is very important. And then I would share my screen, and I hope that you are able to see my presentation. My presentation will be a review of where we are with the carbon capture technology for application on board of vessels. The carbon capture technology is established for land installations with a quite high technology readiness levels. So the technology exists, it is applicable. What we try to do here with is to apply the technology on marine vessels, which is a challenging issue, and to try to provide you as much information on the subject as much as we can. Collecting data on where we are in in the marine world, clearly we need to see that the fuel consumption and consequently the carbon dioxide emissions have been increasing through the years. And the main remark that we can make based on data collected from the United Nations is that the merchant segment is the segment which is contributing the most. And in this merchant segment, we distinguish three major categories: container ships, bulkers, and tankers. And clearly, the indication is that the emissions from all three specific segments are quite similar and quite significant. So what we need to do is to reduce these emissions and revert the trend, which is indicating that in spite of the COVID period, the emissions are continuing increasing. I do have a slide which might be a little bit too busy, but the slide gives a very good overview of where we are at the marine sector. 37,000 ships. The overgreat majority is based on conventional fuels. And every year, what we supply as new is approximately 1,300 ships. So in order to replace the 37,000 ships with ships of new technology, it will take a considerable amount of time. Another important comment is that if we see the fuel consumption, right now, the fuel consumption of the conventional fuels is 220 million tons per year. And in order to replace that quantity by the new synthetic fuels and the so-called advanced low emission fuels like methanol, ammonia, and hydrogen, we would need very significant quantities. And clearly, at the year 2024, 2025, during our period, the availability of these fuels is the problem. So if we talk about changes in the marine sector, clearly the expectation that we had that the new fuels would solve the problem needs to be seen very carefully, because we are not producing, we don't have enough green fuels which will help us invert the trend and improve the environmental performance of the marine sector. Moreover, several of those fuels are required also by other sectors, so we are not the only users of those fuels. And clearly, we see that the fuel transition will take some time, so we are expecting that the new fuels will play a role, but to put also a lot of emphasis on other technical options that you see at the middle of the slide, which include energy-saving technologies, wind assist propulsion, and the onboard carbon capture and storage systems. So carbon capture and storage systems is the subject of today, and it is a way of improving the environmental performance of our vessels. If we see the situation with the fuel and the increase in energy demand year by year, based on an assumption of this increase, clearly we would need to see that the fossil fuel is going to stay for quite a significant amount of time. So we don't replace the vessels fast. The new fuels, methanol, ammonia, are coming at the late side. The reduction of emissions needs to take place sooner. And the available solutions that we have are the solutions indicated in the at the middle of the slide: carbon capture, energy efficiency improvement, biofuels, wind propulsion. These are the solutions that we have in our hands. The solutions have two advantages. We can start immediately the decarbonization. We don't need to wait. And the second fact is that they are applicable to both new built and existing vessels, because as we've seen earlier in the slide that I've shown, 1,300 new vessels will not be sufficient. 1,300 new vessels per year are not sufficient to change the trend. We need to do also actions on retrofitting to existing vessels. If we see the legislation is distinguished by compliance measures like the IMO MARPOL carbon intensity index, where vessels are distinguished in 5 categories. We need to say that unfortunately till now the legislation has not been advanced significantly to incorporate the onboard carbon capture rules. We are expecting that this will happen in early 2025, but we see that the regulation is not helping us driving the activities correctly. The regulation will be arranged, will come, but we don't have right now the rules fully applicable. If we see now the rules from the European Union, the legislation on the EU ETS, that many of you are quite aware. Yes, for the EU ETS, there is a provision that no allowance are needed to be paid for carbon capture, provided, of course, that a few measures are followed. So the EU ETS is recognizing carbon capture, but the Fuel EU, unfortunately, is not yet recognizing the carbon capture as a way of improving the emissions. What I'm trying to say is that the legislation is underway, and we will need to have the legislation supporting the actions for implementation of new technologies. Another important aspect that we need to mention is that if we see the situation with the vessel design, large vessel designs done like the container ships in the picture that is shown above, one of these container ships is using 250 tons of fuel on a daily basis, and it produces 3 times more, 3 times that quantity in carbon dioxide. 1 kilogram of fuel produces 3 kilos of carbon dioxide. That means that also this important aspect needs to be taken into account, that you need to design the vessel correctly, and you need to be sure that the interaction between the engine, the other systems on the vessel, and the carbon capture works on the best way, supporting the effort to capture and store the carbon on board of the vessel. So you need space. You need also to provide additional energy in many cases to be able to convert, to liquefy the gas, and all these are issues which need to be taken into account by all disciplines in the marine world. There is a pre-combustion capture as a way forward. This is applicable only on LNG vessels. It's a solution for LNG, where actually the LNG, before entering into the engine, a partial quantity of the LNG can be converted to hydrogen. This creates carbon dioxide, which needs to be stored separately. But in our case, we are talking primarily about the post-combustion carbon capture, where the gas emitted from the main engine is executing a process on board of the vessel, and then the carbon dioxide which is collected is stored separately. So this is the main subject of the presentation of today, and the two presenters will give you quite a lot of details on the subject. I needed to mention that there are currently quite a number of pilot projects. One of these projects is the project Remarkable. It is supported by a number of companies. You see the main parties involved at the upper side of the slide. What I would like to say, what has been shown and published from this work is that in order to reduce the carbon dioxide, you need some additional energy. So you are increasing the fuel consumption, and this is actually needed in order to liquefy the gas. At the end, you have a significant advantage of carbon capture reduction. However, you have also an increase on fuel consumption. How much is this increase? This depends, of course, on the application, depends on the way that you have sized the system, and depends on the fact that on a new build, you have more opportunities than for a retrofit project where the systems are already sized. Personally, I've been involved in quite a few activities where we tried to find out the cost of the system relative to new alternative fuels. So we did some work where the McKinsey Institute tool has been used, comparing the projection of the fuels of the new synthetic fuels with carbon capture. So what we see is that the cost of carbon capture is an issue which needs to be addressed. We expect with the pilot projects that we have in front of us that the cost will be significantly reduced in the coming period. My personal view is that carbon capture, together with energy saving devices, can be integrated, providing a solution. So on this graph, you see the carbon index, the carbon intensity index, where actually you have a vessel that at the initial time can fulfill the compliance requirements, but through the time, due to the reduction of the emission indices, the vessel has a problem. And then you need actions. The actions can take place every 5 years when you have dry docking, where a combination of measures where carbon capture plays certainly a potential role can allow you to reduce to improve the vessel, reduce the carbon dioxide emissions, and fulfill the requirements of the authorities. I would keep the conclusions for later, and this is my introduction on the subject, and I give this speech to Joni to go through his presentation. Thank you very much.
Yes, thank you very much, Elias. I can start to share the screen or the presentation. Just a moment. Here, I hope you can see.
Yes.
Okay, so first of all, thank you very much for this opportunity to come here and present our carbon capture technology. My name is Joni Uolamo, and I am the product manager of Langht's onboard carbon capture system. Initially, our managing and commercial director, Mrs. Laura Langh, was going to attend this meeting or webinar, but unfortunately, she was not able to today, so I'm here to substitute her and to doing my best to give a good presentation and picture of our technology. So starting with Langh companies, we are 4 Finnish sister companies dedicated to the maritime industry. First of all, Langh provides different kinds of technical solutions to the shipping industry, including ballast water management system, SOx scrubbers, and now also onboard carbon capture. Then we have Langh, which is a ship owning company, owns over 10 vessels that operate in different areas, including the Baltic Sea. And then Langh Cargo Solutions, which is dedicated to providing specialized containers. And then Hans Langh, which is a cleaning services company, providing services for ships and other industrial applications. Going to the onboard carbon capture system, we have now had our product development project ongoing for around 2 years now. And this slide is about the background of the development. So as Elias also explained, most of the carbon capture technologies apply a two-step process where you first capture the CO2, usually with a chemical solvent. And then the second step is releasing the CO2 from the solvent in a desorber, after which you can compress and liquefy the CO2. But these are all energy intensive steps. And one of the main starting points in our project was to minimize the energy consumption. And one way of doing this is to turn the CO2 into solid form. And then pressurized tanks are not needed. And you can basically do the regeneration on land instead. And since a product, stable solid product is produced, it also opens up new possibilities what you can do with that CO2 containing chemical. And in the beginning of the project, when we considered different chemicals that could be used, we looked at the logistics and experience and proficiency, how well established different chemicals are in the maritime industry, and also the production method of that specific chemical, because this is important from a life cycle assessment perspective. When you capture CO2 and produce a product which can be utilized, it is important that the chemical that is used is also produced with minimized emissions. So based on these factors and some laboratory experiments, we concluded that sodium hydroxide or caustic soda is a good option for a number of reasons. First of all, sodium hydroxide reacts strongly with CO2, and the reaction actually can produce two different products, sodium carbonate and sodium bicarbonate, depending on the reaction conditions. But sodium carbonate is formed much more fastly, and the reaction kinetics for this reaction, which is shown here on the slide, is much faster, which really reduces the equipment size. Therefore, sodium carbonate is preferred in our technology. And one particularly important factor is that sodium hydroxide is produced by electrolysis of sodium chloride, which can then apply green electricity. And this is important from a life cycle assessment point of view. So the process is rather simple. We have a capture unit where we direct a part of the exhaust gas, and then we have countercurrently flowing aqueous solution of sodium hydroxide, and they form together sodium carbonate in the capture system. What you can do with the product sodium carbonate then? Well, there are a number of international applications for this product, for example, in glass manufacturing, detergents, pH regulation, water softening, and exhaust gas cleaning. And exhaust gas cleaning means in this context, for example, so-called waste-to-energy plants, where you burn plastic waste, low purity fuels, basically, and they can form different kinds of acidic components in the exhaust gas, and they have to be neutralized some way. So that is particularly interesting way of utilizing sodium carbonate, because the product purity requirements are rather low as well. The second option is, of course, regeneration, which can be done on land. And this is shown here in these two reactions. First, you decompose the sodium carbonate, and then you dissolve the sodium oxide in water, forming sodium hydroxide again, which can be further used to capture more CO2. But this first reaction requires rather high temperatures, and due to the market value of the sodium carbonate which is produced, we have been focusing on carbon capture and utilization concept where you can sell the product. This also makes sense from an economical perspective. Some technical details and numbers of our technology. So basically, because we are not regenerating the solvent, we always need more sodium hydroxide to capture more CO2. And this number is given here on the left-hand side. You need around 3.5 tons of 50% industrial solution of sodium hydroxide to capture 1 ton of CO2. And at the same time, you produce 30% solution sodium carbonate in amount of 8 tons per ton CO2. We have a pilot plant on one of Langh's vessels, and we have been operating with it from last spring. And these tests have shown that the energy that is required to the capture step falls into this range. And this is quite marginal due to the fact that we do not regenerate the solvent and we do not compress the CO2. So this includes basically the exhaust gas fan and then the liquid circulation pump. And this all leads to the fact that about 42% of the dry product sodium carbonate is CO2. Here underneath you can see the one diagram showing how much space is needed for the product when it's produced. So if we take, let's say, a capture unit that captures 600 kilograms of CO2 per hour, this can mean, depending on the vessel, around 20% of the total emissions. And you operate with that vessel around 100 hours. So it makes then 60 tons together. And you can read from the diagram that the amount of space needed is then about 400 cubic meters. And yeah, basically, when you store the sodium hydroxide or caustic soda as well, basically same storage units can be used. So here you can see that the sodium carbonate storage need is then the final determining one, which determines how much space is totally needed. As I mentioned, we have a pilot plant on one of Langh's vessels, and here are two design pictures of it. So it's a modular structure based on 5 different modules. At the bottom, we see a liquid containing module where we have the solution, and then it's circulated to the top of the capture unit. And then we have 3 middle modules with packing beds and nozzles, and then of course a demister on top of the unit. And it's attached to the main exhaust gas pipe of the vessel. And if you look at the picture on the left-hand side, you also see a SOx scrubber underneath the capture unit. So that is used to capture the sulfur emissions, or most of the sulfur emissions. And then the more pure gas is directed into the capture unit, or a part of it at least. And unlike the pilot plant, in full-scale carbon capture systems, we have slightly different way of operation. Instead of only one liquid container, we have 2 process water tanks, which can be used alternatively, so that you start with one process water tank and a solution, fresh solution in that. And at the same time, you can empty the other one and fill with clear or fresh solution. And then you do basically the same the other way around. So this is the way of operation when you want to operate continuously. Then we also have, of course, CO2 measurement before and after the capture unit, and also exhaust gas flow measurement. So based on these values, you can determine how much CO2 has been captured in the unit. And the same can be proven by analyzing the product, of course, when analyzing how much carbonate has been produced. Depending on the fuel that is used, you need different kinds of systems for pre-treatment of the exhaust gas. With HFO, you basically anyway need a scrubber to get the most of the sulfur out of the exhaust gas, and then with MGO, the situation is basically quite the same. And for LNG, no scrubber is needed because the sulfur content is lower, but some kind of cooling is needed because the carbon capture system operates at about 40 degrees or 40 to 50 degrees Celsius. So the exhaust gas has to be cooled down in some way. That is everything I have in this presentation. Thanks for listening.
And thank you, Joni, for this very interesting presentation. There is a question from the audience. Do the costs include also further storage disposal of the CO2? Can you say anything related to the cost?
I can say so. Basically, the whole idea, or one of the main principles in our technology, already from the beginning, was that we want to create a business model where the whole technology is not dependent only on the regulation. So basically, it has been proven that the sodium carbonate that is produced from our pilot plant can be used in several applications. Yeah, and basically, you get value from the product as well. So it's an equation of different, basically, money flows, and the business case is built mainly on the caustic soda price, sodium carbonate price, and then in the future also the regulation, what kind of benefits you can achieve on that regard.
Okay, but the expectation is that the potential owner using the system is receiving some money back for the CO2. The CO2 becomes a kind of a commodity product.
Exactly. That is the idea.
Yes. Can you also tell us something related to the harbor infrastructure you need? Is there any specific effort and specific need for carbon infrastructure at the harbor?
Actually, I see at least it a bit easier than with pressurized CO2, because caustic soda, as I mentioned, is an established chemical in the maritime industry, also used in SOx scrubbing, for example.
Mm-hmm.
So the infrastructure is already there for that chemical, and sodium carbonate is pretty much quite similar product with lower safety requirements than caustic soda, and the infrastructure doesn't in that way require big differences or big changes compared to liquefied CO2, for example.
Mm-hmm.
That is at least my understanding currently.
Yes. By the way, there are additional questions, and I would will have the opportunity to discuss it all together. I believe some of the questions could be also requiring an answer from Dimitris. So I would stop the question around right now here, and of course we'll have 20 minutes later to cover all questions from the audience. I need also to add that we have already the polls being opened. So we would encourage you to help us providing an answer to the questions at the polls. Thank you. And I give the floor to Dimitris for his presentation. The floor is yours, Dimitris.
Thank you, Elias. Just a moment. Okay. Thank you, everyone, for the invitation to participate in this very interesting webinar, and a huge welcome to our audience. I am Dimitris Koutsaftis. I am a senior scientific consultant at ERMA First, and I am acting as the R&D project leader for our carbon capture and storage project. A few words about ERMA First. The ERMA First group is a global leader in sustainable technology, offering advanced solutions in ballast water treatment, water and wastewater treatment, as well as energy-saving devices, decarbonization, and big data analytics. Our products include ballast water treatment, water and wastewater treatment, energy-saving devices, decarbonization solution, as well as big data analytics. A few words about our timeline. We were established back in 2009. In 2010, we did our first land-based tests at NIOS. We got our IMO approval in 2011. And in 2017, we got our US Coast Guard type approval, which was a huge milestone for us, which led to our huge growth from that point on. In 2018, we launched new offices both in South Korea as well as in China. And then the acquisition of companies started. In 2019, we acquired BOLETIS, a data analytics company. In 2021, we acquired another ballast water treatment company, One Tank, as well as a traditional wastewater, marine wastewater equipment manufacturer, RWO. And in 2024, only a few months ago, we acquired a second ballast water treatment company, EcoChlor. According to Clarksons, ERMA First has 15% of the market share of the global fleet in ballast water treatment systems, and is number one in market share again for the global bulk carrier fleet. We operate in 46 countries through a wide sales and service network. And regarding our ballast water treatment products, the one on the top is our top-selling product, the ERMA First Fit. On the bottom, you can see the One Tank solution, which is suitable for small vessels, tanker after-peak tanks, and super yachts. This is our new product, the ERMA First Flow. It's currently under testing in order to get its type approval. It's an ideal solution for new built vessels for high capacities. It's again an electrochlorination solution such as the ERMA First Fit, although without a filter. Regarding our decarbonization solutions, we have our ERMA First Blue Connect, which is our alternative maritime power product, which in essence has an interface when the vessel is at berth in order to get power from the grid at the port instead of running the auxiliary engines. We moved on to our energy-saving devices, and specifically the FlexCap, which is already available in our product portfolio, and the Flex Ring and Flex Fins, which are coming. These are devices that are installed on the vessel, and their purpose is to optimize the flow and in such a way in order to reduce power consumption and optimize CII and EEXI. And we move on to our carbon capture solution, where we have focused on two technologies. Both technologies are based on absorption. We have our amine-based solution, followed by liquefaction of the CO2, as well as our calcium hydroxide solution, which is a much simpler method, especially designed for vessels doing very small voyages for short shipping. Today, I will speak to you exclusively about our amine solution, which is again based on absorption. And absorption as a whole is the most widely spread technological approach for capturing CO2. It has significant advantages compared to other technologies. Its main advantage is that it can be retrofitted to existing installations with minimal modifications and a very high technology readiness level. And the types of absorption, first of all, we have the chemical absorption, where there is a reaction of the CO2 with the chemical solvent. So in this category, we have the use of amine-based solvents, as we have discussed up to now, the use of inorganic solvents such as caustic soda, potassium carbonate, etc., as well as ammonia-based processes. And there's also the case of physical absorption, where there is no chemical reaction of the CO2 with the solvent, but only dissolution in it. If you look at this chart, at the vertical axis, you have the partial pressure of the CO2 in the feed of the chemical plant, and on the horizontal axis, you have the partial pressure of the concentration of the CO2 at the inlet of the plant. So, the marine industry lies, the emissions from marine engines lie in this region here. So it is quite obvious that the amine technique is the one that gives the highest selectivity for capturing CO2 from marine engines. So how does absorption with amine-based solvents works? It's basically a cyclic absorption and desorption of CO2, usually performed by altering the temperature, doing the temperature swing, as we say. High CO2 absorption capacities between 90 to 95% have been reported in the literature and have been demonstrated during various pilot plant campaigns, as well as actual plant operation. However, this high absorption rate comes with a cost, and this cost is the high energy required in order to regenerate the amine and strip CO2. Various types of amines and amine blends have been proposed and used in order to minimize this energy penalty. And traditionally, the use of monophenol amine is considered as the baseline standard for post-combustion carbon capture, and it's used quite extensively even now. Of course, capturing CO2 using amines is not a new technology. It goes back to the 60s and 70s. So the big challenge is the marinization of the technology. And certain challenges had to be addressed, such as the minimization of footprint, the variation of the exhaust gas composition and the flow rate, the operation under marine conditions, and more specifically inclination, vibration, etc. The complexity, because as you will see, we are speaking about significant complex equipment. The exhaust gas pretreatment, which is necessary in order to bring the exhaust gas to the appropriate conditions in order to react with the amines, and of course the minimization of heat requirement for the regeneration of the amine. So this is the flow chart of a typical amine-based CO2 plant. On the left side, you can imagine the exhaust stack of the vessel where we draw a slipstream. We are not treating the entire gas flow. We are only treating a slipstream, approximately 40 to 50% of the flue gas emitted from the main engine is directed to the pretreatment stage here. This is the pretreatment stage, which consists of a direct contact cooler, which is a direct analog to a shock scrubber, whose purpose is to bring down the temperature to the region of 40 to 50 degrees, remove and knock out any SOx and NOx contained in the flue gas, remove particulate matter, which is also very important for the proper operation of the unit, and also saturate the flue gas with water vapor. After this pretreatment has been completed, there's an optional filter that can be employed in case there is a significant amount of particulate matter still present in the flue gas. This is an optional equipment. After this treatment, the flue gas enters the absorber. It comes in contact with the lean-in CO2 amine indicated by the orange arrows here. The reaction takes place in the packed bed sections of the absorber. The rich in CO2 amine collects at the bottom. It is directed through the rich pump to this heat exchanger where it's preheated to approximately 100 degrees and is led to the stripper where the amine comes in contact with stripping steam generating from the boiling of the amine itself. So there is steam coming up from the bottom of the stripper, comes in contact with the rich amine, and so the CO2 is released. This is a feature of the amines. High temperatures favor the release of CO2. The rich in CO2 stream goes to the top of the stripper. It's cooled down to approximately 40 degrees here. The water that's condensed through this process returns to the plant, and we have a product CO2 with a purity of approximately 96 to 97% pure, ready for liquefaction. The lean in CO2 amine, the one has been regenerated, is accumulated to the bottom of the stripper. It's relatively hot, has a temperature of approximately 110 to 120 degrees. It is used through this main heat exchanger to preheat the rich amine, as we said before. This one cools down to approximately 60 degrees here and 40 to 45 degrees here and returns in order to complete the process cycle. Above the absorber, there are usually one or two water wash sections. These are there in order to knock out any amine emissions, as well as to bring the plant to keep the plant in water balance, because the reaction of the flue gas with the amine is exothermal, so a significant amount of water is being continuously drawn from the amine towards the exhaust gas. And for this reason, the water wash sections cool down again the exhaust gas to 40 degrees, 40 to 50 as we said here, 40 to 50 here as well, in order to keep the plant into water balance. Regarding the CO2 storage options, there are basically two options: either compress it in high pressures or liquefy it. And out of the two solutions, the one that is most practical for onboard use is the solution of liquefaction, due to the fact that CO2 has the highest possible density, so it occupies the least possible space on board. So, coming to the capture part of board, the CO2 that comes out of the stripper is compressed in a two-stage compression. The pressure here rises to approximately 15 to 18 bar. So the CO2 is firstly compressed. Any CO2, any water is after the cooling processes is separated and returned to the ammonia plant. Again, there is a cooling process bringing down the temperature of the CO2 stream to approximately 10 degrees Celsius. It's then directed to an activated carbon bed where volatile organic compounds are knocked out, and subsequently to a desiccant dryer where moisture content goes down to less than 30 ppm in the CO2 stream. And after this, the liquefaction and purification stage, further purification stage takes place. This is a process where non-condensable gases such as nitrogen and oxygen trained in the CO2 stream are knocked out, and we have a liquid CO2 exiting the plant with a purity of 99.9% food grade purity. How the plant sizes procedure takes place, we have the vessel details submitted by the client. We have a pre-assessment done internally through our relevant department. We can run a techno-economical feasibility study regarding the impact of the plant, especially in terms of CIR reduction over the years, as well as provide a clear estimate of steam and power and fuel consumption. And then a decision along with the vessel owner is taken on which system capacity is installed. We have available capacities ranging from 500 kilos to 2,500 kilos per hour of CO2, and available tank sizes starting from 50 cubic meters and going up to 400 cubic meters. The advantages of our system is that it has an extremely low footprint due to the special design of our absorber and stripper modules. The performance of the absorption and the stripping are unaffected by the shipping inclination. We have the possibility to install the system in vessels already equipped with shock scrubbers. Our installation is modular and consists of several skids that are interconnected. An exhaust gas economizer is used as a sander in order to reduce steam consumption to an absolute minimum. And of course, the purity of the CO2 produced is of food grade, as I mentioned earlier. These are some photos of our pilot plant. This is a photo of all the arrangement of the equipment, and this is how it looks in the actual world. It's under construction at the moment, and it's expected to start at the operation at the beginning of March. So thank you for your attention.
Thank you. Thank you, Dimitris. Actually, I had a question regarding the application of the system, but you mentioned that at the end of your presentation that there is an application coming on
Yes.
on board of a vessel.
Yes.
Yes.
We have a pilot plant. It's nearly complete in its construction part. And we expect the installation and commissioning to take place at the beginning of March.
Okay, thank you. Then you mentioned also the technology readiness level of the application with the technology readiness level for land installations is indeed considered as quite high.
Yeah.
And now the main issue for us is the application, the specifics of the application in the marine world, where you have the main engine, which is in reality we are requiring more power to feed the system. We have different conditions on the main engine. We have the issues of the storage, the issues of transportation. So the overall picture for marine might be different than the picture for land installations, where the technology can be considered indeed as reaching a series production and reaching a kind of maturity. So the numbers that you mentioned of technology readiness level 6 to 8.
Yes. We are at the moment, since we are speaking about a pilot technology, we are speaking about the TRL of 7. Okay.
Okay. Yes.
So, as I mentioned in my presentation, there are several challenges that need to be addressed for the marinization. For example, you will rarely see an exhaust gas economizer integrated in an amine plant on the industry.
Yes.
You will rarely see measures taken in order to optimize the plant operation due to a variation in the load, in the concentration of the CO2, or in the amount of flue gas that needs to be drawn. Also, the way that we perform the absorption and stripping is different compared to standard absorbers and strippers.
Yes.
So these are all measures that we have decided to take in order to make the technology more marine friendly.
Okay.
So it's the marinization part that limits the TRL. Yes.
Okay. The time comes to see the polls, and then will be returning to the questions. I would I see already that Joni has answered some of the questions. I would ask you, Dimitris, to have a look at the questions as well, to the time that we are reviewing the polls, hoping that the polls are ready. I think that the organizer will add the polls on the results of the polls on the main screen. So since I don't see the results of the polls right now, it is good to go through some of the questions from the audience. There are a lot of questions related to the impact of carbon capture to the main engine. The fact that you use the carbon capture, does it have an impact on the engine efficiency?
Can I answer?
Yes, of course.
No, there is no impact. There is only a slight increase in fuel consumption of the order of 5 to 10%. There is no impact on the performance because we draw a slipstream. The remaining of the flue gas goes to the top of the exhaust gas, so there is no impact on the performance. Only this increase in fuel consumption, which is imperative for both for the capture and the liquefaction plant operation.
Yeah, it's the same case for our technology, because we also have a bypass flow, and we utilize an exhaust gas fan to deliver the wanted amount of exhaust gas into the capture system.
May I ask both of you, what is, according to your opinion and for your applications, the design power level of the engine? I mean, you mentioned also, Joni, that you have exhaust air bypass. What is the power level that you are addressing as a design power for the application?
You mean the engine load or?
Yes.
Okay, so normal operation, depending on the vessel, the operational
Yes.
engine load is of course a bit different, but yeah, normal operation. About, depending on the vessel, it can be between 50 and 90%. Yeah.
Okay.
Same for us. We're operating exclusively under seagoing conditions, where the engine load is relatively stable, in order to avoid any fluctuations, both in the exhaust gas flow as well as, so in order to ensure that there's sufficient flue gas to draw and do the treatment, and verify that the composition of the exhaust gas is relatively stable.
Yes. Okay, we might return to this question, but let us see the results of the poll one by one. The first question was to the audience, to understand the audience. How familiar are you with carbon capture technologies for maritime applications? Then the overwhelming majority, 63%, indicates that the audience is somewhat familiar, 21% very familiar, and 28% not familiar at all. So we are in the category primarily of somewhat familiar, but more information is required and more knowledge of the technology is required. Okay, I believe this is quite clear. Can we proceed to the next poll, please? Yes. Now, this is interesting because the same question has been answered on exactly the same way some time ago. And the question is, what do you consider as the biggest challenge for implementing onboard carbon capture? And then you see the answers. Cost and financial investment is the largest with 35%. Technology readiness follows with 18%, together with the lack of harbor infrastructure and space constraints on board of the ships. So we see 18%, 19%, and 20% for the answers B, D, and E. So they are quite similar. And there is an 8% given to the regulatory compliance. So do you wish to comment into this poll? Either Joni or Dimitris?
Do
you have something to say, Dimitris? You can start if you want.
Yes. Thank you. The biggest challenge for implementing, in my opinion, and I think it's the opinion of our companies, the lack of infrastructure. Okay, the question as to what happens after you capture it and store it on board is the main question to be solved for the wide deployment of the technology.
Yes. And I think, in my opinion, right now, at this moment, the most challenging is actually regulatory compliance or regulatory frameworks overall. Because with our technology, when we develop a carbon capture and utilization technology, particularly, the regulatory frameworks are being established, and most focus has been on carbon capture and storage. So it has been probably most challenging to try to develop a new technology considering all the technical details, but also the regulatory frameworks and how the technology will be considered in the future, because this also affects the feasibility of the technology. So at this moment, regulatory compliance, I would see as the most challenging one.
I would present also my opinion, and again, it is an opinion among all others. I need to say that I'm very happy to see that there are quite a few pilot projects. I'm calling them pilot because they are the first applications of the technology at the field. The industry needs these projects, needs the applications, and through these applications, we are learning. We are creating a know-how which will help us that the upcoming versions of the product will address the issues on the cost, technology readiness, and of course the space constraints is something which can be solved easier on a new build than on existing vessels. But the fact that we have quite a few pilot projects around is a very positive signal that there is interest in the technology. And as you apply those projects, we are learning through this process with as outcome that our know-how coming from this from the field experiences will be reflected to the new generations of the products. I agree also with Joni that the issue of carbon infrastructure is, and also Dimitris, the issue is very significant, because if this does not exist, it's very difficult to proceed. So it is a system. It's not only one part of the puzzle that we need to address. Is not only the system on board of the vessel, but you need to create the ecosystem where you are able to offload the captured CO2 and to use it on a proper way. The infrastructure required in harbors is quite significant. And of course, this will become an even bigger issue as the number of applications is increasing. So it is an issue which needs to be addressed by the total community. Is not only applying the technology on the vessel, but how this technology is going to be integrated in the marine ecosystem.
I'm sorry, may I answer to one very good question here in the chat? Manuel Pallister asks about utilization of CO2, and this is a very good question, also very critical one. That is always good. So the question is, with carbon capture and utilization storage, how can any use of CO2 work? As the purpose is to reduce the CO2 footprint in the atmosphere. If it realizes CO2 in any way, releases CO2 in any way, then it fails to work as carbon capture. That is a good point, but I would like to point out that it has to be considered on a broader scale, I think, in my opinion at least. So, for example, sodium carbonate is typically produced by extracting sodium carbonate from the Earth's crust. So basically that comes from the ground, and in a conventional way, if you use that sodium carbonate the way the CO2 is released, you basically release fossil CO2. But by applying a sodium carbonate product that has been produced by recycling the CO2 emissions from the vessel's exhaust gases, you're basically replacing the conventional one with the low carbon alternative. And it is important to note that at that stage, you are not only decarbonizing the shipping industry by capturing CO2, but you're also decarbonizing the sodium carbonate industry where the sodium carbonate is used. So in that way, you basically end up releasing less CO2 than in the beginning. So of course, this is good thinking that if the CO2 is captured, why release it back into the atmosphere? But by applying this kind of technologies, this can lead to establishment of carbon capture technologies, and also more sustainable alternatives in other industries as well. So I at least use that kind of thinking in this case. Thank you.
Okay, thank you. By the way, can we proceed to the next poll? There are a few. There are one or two more. Yes, did we discuss this? Yes, we discussed it. Indeed. Okay. Any comment on the polls? Any final comment on the polls from Joni and Dimitris? Is this reflecting your experience as well?
Regarding this part, no. I voted for A, actually. So I am quite certain that CO2 capture is one of the key, if not the one that has the highest impact compared to all other technologies regarding reducing CO2 emissions.
Yes.
I also agree. CO2 capturing is something that can be done in short run, and also have a big impact in larger or longer run. So yeah, for sure, this is one of the solutions. Of course, there is no silver bullet. You cannot solve this big problem with only one solution. So therefore, I think this is part of the solution, so to speak.
Mm-hmm. Yes. Actually, thank you. Going through the questions, I believe that quite a few questions have been responded, have been answered by both Joni and Dimitris. Yes, I think we'll go through the questions once again later, and we could provide an answer if a question has not been answered by us during the presentation. There is a last question, Joni, by Eric. What is the capture rate per hour of the Langh system presented?
Yeah, so the pilot plant has a slightly lower capture rate than 100 kilograms per hour. So we are able to go currently with our design up to 1,500 kilograms per hour. And we are now advancing in increasing the backing bed surface area for the capture system to enable even more or higher mass amounts of CO2 to be captured. But the pilot plant has a capture rate of about 100 kilograms per hour. And our process is interesting in that way that the capture rate is actually dependent on how fresh the solution is. So it's a kind of a dynamic process where the capture rate is higher in the beginning, reaching values of about 200 kilograms per hour. But once the sodium carbonate starts to accumulate in the solution, the capture rate starts to decrease, reaching some 50 kilograms per hour in the end. And the overall is around 80 to 100 kilograms per hour. Also, depending on how strong solutions of sodium carbonate you produce, the stronger solutions you want to produce, the lower is the capture rate. So it's a dynamic process.
Yes. Can I ask from my side, when you see the vessel segments, container ships, tankers, bulkers, special vessels, where you see the majority of applications in the future, at least in the merchant segment? Any thoughts? Also, you see the majority of applications on smaller vessels, medium-sized, large-sized vessels, where you see that we need to focus our efforts.
Can I answer?
Yes.
Personally, and as ERMA first, basically everywhere. Of course, every vessel has its limitations. For example, bulk carriers have small boilers. Okay, this is a limitation for the system, but doesn't mean that the system cannot be installed. We have done a feasibility study producing some really good results on a bulk carrier, even though with a relatively smaller size. And more, to give you to focus on our product portfolio, our capacity range is specifically designed in order to cover both smaller vessels and larger vessels. So we believe that carbon capture cannot be limited to a certain area. There can be solutions both for small vessels, big vessels, vessels doing short shipping, vessels traveling 20 or 30 days in the ocean. A solution can be applied to anything.
I agree in this, but I would like to add that depending on the vessel, the solution can be different. Our technology is most suitable for vessels with regular ports for discharge and so on. So it has to be kind of considered case by case or case by case. And yeah.
Yes. You are right. Well, I've been once again through the questions. I believe that we have answered on most of the questions. Probably one or two have escaped, but it does not matter so much. We will sit together and to give an answer to the questions which might remain unanswered. I would would have the opportunity to have some concluding remarks. So can you start from you, Joni? Do you have any concluding remarks?
Maybe that carbon capture is being developed. There is a lot of technology development going on, and I would like to emphasize that solving this problem is of course very challenging, and there is a lot of chemistry, a lot of engineering back there, even though it might seem very simple. Yeah, a lot of actions are being done, and depending on the case, different solutions can be applied. There is no silver bullet for solving this big problem.
Dimitri, you?
I endorse 100% what Joni just said. From our perspective, we need a bit of a boost in the part after the storage of the liquid CO2. This will unlock the deployment of the technology and its widespread use in the maritime sector.
Yes. From my side, I have some concluding remarks from my initial presentation that I propose to go through. And what I tried from my side to bring as a message is that we have a challenge in the maritime sector, the path to decarbonization, the expectation that the biofuels and synthetic fuels would solve the problem is found not to be time-wise appropriate. The supply is and seems that it will remain insufficient. Fuel prices are volatile, and the introduction rate of the new build is quite low to keep following the emission targets. So we have a problem which needs to be addressed for both the new build and retrofit, and the solution fits both. So this is my main comment. Onboard carbon capture seems to be a good option, a good alternative to reduce carbon emissions. One important thing is that all fuels which have a carbon content are possible to be addressed. So from that point of view, we are addressing all fuels except ammonia and hydrogen. And another possibility is that onboard carbon capture can be well combined with other energy-saving technologies. So if we talk about the energy increase due to the needs of the system, we need to find a total solution, an integrated solution where the overall performance of the vessel would be benefited the most. And I mentioned also before that the very positive issue is the fact that to have first applications of technology, of course, from both companies of yours, but also many other parties are working on the technology. And this is encouraging. It is allowing us to learn. We are enhancing the technology know-how and, of course, the productionization of the solution. This would mean that the cost and the technical issues related to integration will find the final solution as we go through. So this is my lesson learned from my view of the field. So I believe and I hope that the audience remains positive to the technology. I would like also to take the opportunity, closing this session, to inform the audience that the BS Group is running the second Ship Propulsion Summit in Rotterdam, in the Netherlands, on March 20. The first Ship Propulsion Summit was in Athens in 2024. So the new one is in Amsterdam, and would be very happy to see you there. Many thanks. Thank you for attending, and I wish you a nice, a good continuation of the day. And I hope that the 1.5 hours that we spent together was useful to increase your understanding on the onboard carbon capture technology. With my thanks to both Joni and Dimitris for their presentations, and the thanks to the BS Group that they have organized the session of today. I propose to close the session. Thanks a lot.
Thank you very much from my side as well.
Thank you, everyone.
Thank you.